All right, so get this. We're diving into like the Beyonce of AI papers today.
Oh, wow.
Yeah, super famous, super influential, and it totally like changed everything.
Right. I'm intrigued. Lay it on me.
It's called Attention is All You Need,
Hmm. Catchy title.
right? And we're doing this deep dive because our listener wants to know how we got to like Siri and Alexa and all that AI stuff we use every day.
So basically, before all that, we didn't have those things. And this paper is like the foundation.
Exactly. But what was so groundbreaking about it? What were the limitations back then?
Okay, well, before this paper, those large language models were mostly built on RNNs, recurrent neural networks.
Oh, RNNs, come on.
Yeah. And imagine reading a book, but only one word at a time, like each word influences the next one and so on. But they were slow, and it was really hard for them to remember information from earlier in a sentence.
So like trying to understand a whole novel by reading one word at a time and then forgetting it?
Pretty much, they just couldn't handle the complexity of language at the scale we needed.
So how did Attention is All You Need solve this problem?
Well, that's where the brilliance comes. In this paper, introduce parallel processing, like looking at a picture and taking it all in at once. That's what the transformer does with language.
It analyzes all the words at the same time.
Exactly. And that's how it grasps the meaning and context so much better than RNNs.
Okay, that makes sense. But this attention thing, can you break that down a bit more?
Sure. Imagine you're reading and you highlight the important parts.
Oh, yeah, okay.
That's what attention mechanisms do in AI. They focus on the most relevant words and how they relate to each other.
So it's not just reading, but like understanding.
Exactly. And that's thanks to something called scaled dot product attention, a key innovation in the transformer.
Scaled dot product attention. That sounds pretty sci-fi.
It does, but it's actually quite simple. So each word is represented by a vector, like a list of numbers that capture its meaning.
Okay.
And scaled dot product attention calculates the dot product between those vectors to see how similar they are.
Dot product, so it's like math.
Yeah. And the scaling part just makes sure those values don't get too big, which helps with training.
So it's like the model is figuring out which words are BFFs?
Exactly. It's creating a relationship map, highlighting the strong connections.
Gotcha. But there's also multi-head attention, right? What's that about?
Think of it like having multiple attention mechanisms, each with a different focus.
So like different perspectives.
Exactly.
Yeah.
One might be looking at grammar, another at meaning, and another at like relationships between people and places.
So it's like a team of super readers all working together.
Precisely.
But hold on, if it's processing everything at the same time, how does it know the order of the words? Like, the cat sat on the mat is different from the mat sat on the cat.
Good point. That's where positional encoding comes in. They add signals to the data that represent the position of each word, like a timestamp.
Oh, so it's like each word has a little number tag telling it where to stand in line.
Yeah, a very clever way to keep track of order.
I'm really starting to see why this paper was such a big deal.
Oh, yeah. And there's more. It wasn't just about language translation. The authors tested it on other tasks, like figuring out the grammar of sentences, and it did incredibly well.
Wait, it was good at something it wasn't even designed for.
Yeah, they predicted it would be useful for all sorts of tasks, and they were right.
Okay, this is all mind-blowing, but I'm still curious about why RNNs were so limiting.
Well, remember, they processed information one word at a time, like that old book analogy.
Right.
So they couldn't handle long sentences, and they couldn't really take advantage of parallel processing, which is crucial for training those big, powerful models.
So the transformer was a game changer because it could do everything at once and still keep things in order.
Exactly. A truly revolutionary step. And to understand its full impact, we need to look at how it's used in the real world.
Okay, I'm ready for part 2. Let's see how this abstract research paper ended up in our phones and computers.
Sounds good. Let's dive in.
Okay, so last time we were talking about how the transformer model like blew everyone's minds by processing everything at once.
Right, it was a major shift from those old RNNs.
Totally, but we didn't really get into like the nuts and bolts of how it actually works.
True, we kind of stayed high level, but we can definitely dig deeper.
Awesome, because I'm still a little fuzzy on like how it all comes together.
Okay, so imagine the transformer as like a super organized factory with different departments.
Oh, I like that analogy.
Yeah, so first you have the encoder, that's like the intake department. It's responsible for reading and understanding the input text.
So it's like the eyes of the model taking in all the raw data.
Yeah, but it's more than just seeing it. It's actively trying to figure out what the text means, and that's where self-attention comes in.
Oh, right. Self-attention helps it understand how the words relate to each other.
Exactly. So let's say the encoder's reading the sentence. The quick brown fox jumps over the lazy dog. Self-attention allows it to analyze each word in relation to every other word.
Okay, so it's like it's creating a map of the sentence in its mind.
Yeah, like it might notice that quick is closely linked to fox and jumps, so it starts to build a deeper understanding.
That's so cool. And what about those multi-head attention things we talked about?
Right, those are like having multiple teams within the encoder, each looking at the text from a different angle.
So it's like a brainstorming session with everyone trying to figure out the text.
Yep, some might be looking at the grammar, others the emotions, and others the overall story.
This is making so much more sense now.
Okay.
So once the encoder has done its thing, what happens next?
Then the decoder comes in, that's our production team. It takes all those insights from the encoder and uses them to create the output.
So the encoder analyzes and the decoder creates. Got it. But if the encoder is processing everything at the same time, doesn't the decoder get a jumbled mess?
Good question. But that's where positional encoding comes in again, those timestamps we talked about earlier.
Right, the little tags that tell each word where it belongs.
Exactly. The decoder uses those to make sure the output is in the correct order, one word at a time.
Ah, so it's like a blueprint for the decoder.
Yeah, a way to keep everything organized. But the decoder has another trick up its sleeve. Masked self-attention.
Masked self-attention. Now I'm really curious.
So imagine a writer carefully crafting a sentence, making sure it flows smoothly from the previous one.
Okay, I can see that.
While masked self-attention prevents the decoder from peeking ahead at future words. It has to focus on what it's already written and create a logical progression.
Ah, like a built-in editor.
Yep, it's all about quality control. But wait, there's one more piece of the puzzle, the feed-forward network.
We haven't talked about that one yet. What does it do?
Think of it as the finishing department. It takes the information from the decoder and adds those extra layers of processing to make the language sound natural and nuanced.
So it's like polishing a rough draft.
Exactly. It helps the transformer go beyond just being grammatically correct. It adds that stylistic flair.
Oh, wow. This is amazing. We've gone from like zero to actually understanding how the transformer reads, analyzes, and creates language.
And that journey leads us to the most exciting part, seeing how all of this impacts our everyday lives.
Okay, so we've gone deep into how the transformer works.
Yeah, pretty deep.
But I think our listeners are probably wondering, like, how does this actually affect me?
Yeah, good point. Let's bring it back to the real world.
Because it can't all just be happening in research labs, right?
Right. It's actually all around us. You probably use it every day.
Really? Give me some examples.
Well, think about your smartphone. When you ask Siri or Google Assistant something,
Oh, yeah. Okay.
that's a large language model based on the transformer.
So it's understanding my questions because of this paper.
Exactly. It's the brain behind those interactions.
Wow. And what about like Google search?
Oh, yeah, that too. Transformer-based models like BERT are helping Google understand your searches, even if they're super complex.
So it's making search better.
Way better. And don't forget about those personalized recommendations you get on Netflix or Spotify.
Oh, right. How do they know? I love those cheesy rom-coms.
Well, those algorithms are often powered by transformer-based models too.
Mm-hmm.
They analyze your viewing history to predict what you'll like.
So it's like having a personal AI DJ or movie critic.
Pretty much. But it's
Yeah.
not just about entertainment.
Oh, right. Okay.
In healthcare, transformer-based models are being used to analyze medical records and help with diagnoses.
So it's actually saving lives.
Potentially, yeah. And in climate science, they're using them to analyze all that climate data.
Wow. So it's helping us understand and address climate change.
Exactly. It's really amazing to see its impact across so many fields.
It is, but are there any limitations to the transformer?
That's a good question. It's a powerful tool, but no technology is perfect.
Right.
Some people argue that these models don't truly understand the meaning of language. They're just
Yeah.
really good at mimicking it.
Oh, like a parrot who can repeat phrases but doesn't know what they mean?
Yeah, that's a good analogy. And there's also the issue of bias.
Bias, how so?
Well, these models are trained on huge data sets of text and code, and those data sets can reflect biases that exist in society.
Ah, I
So
see.
we have to be careful about that and make sure these AI systems are fair and equitable.
It's like any tool we need to use it responsibly.
Absolutely.
Okay, so as we wrap up this deep dive, what's the key takeaway for our listener?
I'd say the attention is all you need. Paper is a landmark achievement that's had a huge impact on AI and our lives.
It's pretty amazing to think about.
It really is, and it shows the incredible power of human ingenuity.
But it's just the beginning, right? What's next for AI if attention is all we need now?
That's a great question, and the answer is we don't really know, but that's what makes it so exciting.
There's still so much to discover.
Absolutely. Research in areas like multimodal AI is really taking off.
Multimodal AI.
Yeah, so
What?
models that can understand not just text, but images, sound, and video.
Wow, imagine being able to interact with AI in all those ways.
right? Creating art, composing music, even making scientific breakthroughs together.
That's pretty mind-blowing.
It is, and that's the beauty of this field. We're constantly exploring and pushing the boundaries of what's possible.
This has been an incredible journey learning about the transformer, its impact, and what the future might hold.
Yeah, I think our listeners are walking away with a lot to think about.
And hopefully they're inspired to keep learning and maybe even contribute to the next big breakthrough in AI.
Exactly. Who knows? Maybe they'll be the next AI superstar.
Well, that's all the time we have for today. Thanks for joining us for this deep dive into Attention is All You Need.
And thanks to our listener for sharing this fascinating paper with us.
We'll be back next time with another deep dive into the world of AI research.
Until then, keep those AI brains buzzing.